Okay. Uh, Sheila, so here's a standard pulse sequence that we've been talking about here for days. 90-degree pulse. At time tau after the 90-degree pulse is 180-degree pulse. And at time tau after that, we get an echo. Could you explain
Dr.
to us
Francis,
how? Yes.
I'm sorry.
You
I
see?
can't see anything.
That's because I forgot to turn the screen on. I
Thank
bet
you.
that's better. Thank you. Thank you, Yuri. Okay. So could you explain to us how the 180-degree pulse creates the echo?
Okay, so I think when you give a 180-degree pulse, then I think that the vector switches from the z plane to the xy plane. I think no, that I'm off. I don't know. Still don't know.
Boy, I'm such a good lecturer here. Okay, so okay, with the 90-degree pulse, well, before the 90-degree pulse, before any 90-degree pulse, the bulk magnetization vector is pointed along the axis of the main magnet, the z-axis. After we give the 90-degree pulse, we rotate the bulk magnetization vector 90 degrees into the xy plane and it starts spinning around at the Lamar frequency, right? So once it's spinning around the Lamar frequency, we then put a 180-degree pulse, which flips the axis in the xy plane, flips the spins in the xy plane. Okay, not from the z-axis. It flips them in the xy plane. Remember, all the individual little spins are precessing around here in the xy plane. When we flip them, then what turns out then by flipping them 180 degrees, the guy that's spinning fast actually is put behind, and the guy that's spinning slowly is now out in front. So how does that create an echo?
I think I probably should hold back from answering questions. I think I'm done with the question.
I mean, all I could say is that it just introduces new potential energy into the system. I think it's, the echoes are
It's not potential energy.
trying to get back to like a certain baseline state, but the spins, the proton.
You guys are making it much more difficult than it is. It's not that complicated. Michael, how did this diagram help explain why we get an echo?
This diagram is illustrating that the protons are dephasing at different rates, and I think it's due to their magnetic shielding, but they dephase at different rates, some slower, some faster. And when you give them the 180-degree pulse, it causes them to rephase such that they all return at the same time to their baseline, although they are moving at different rates. Just some move back to the baseline faster than others.
Okay, so if we have this race between the tortoise, the bicyclist, the car, the plane, and the rocket, and if we say we trigger the gun and they start off in one direction at a constant speed, each one is constant, but they're all at different speeds, and we let them do that for an hour, and then we tell them turn around and go back again, but keep your same speed. 1 hour later, even though the rocket will travel much, much farther, 1 hour later they will all come back and hit the finish line at exactly the same time, right? As long as their speed going out is the same as their speed coming in. Does anybody have a problem with that? Understand it?
Right. That's all caused by that 180-degree pulse, right?
Yeah,
That
the
sets them back.
180 degree, yeah. This is
Okay.
this is caused by we tell them to turn around and go back.
Right.
But that's what the 180-degree pulse does. They start
Right.
spinning around, they get out of phase. The fast ones are out here in front, the slow ones are back here behind. When we give a 180-degree pulse, now what happens is that the fast guys are now the slow guys. I mean, the fast guys are behind, the slow guys are in front, And at the same time later, they'll all come back and catch up with one another. And then they'll all be in phase. So what happens then, the 180-degree pulse flips all the spins around. So then it would, if the fast guys then become very behind here because they're as far behind as they were ahead before. And then if it keeps going fast, it will catch up to the slow guys, and at time 2 tau, they'll all come together and produce a spin echo. The bulk magnetization vector will no longer be zero in the XY plane. We'll have a rotating magnetization that will induce current in our receiver coil, and we'll get an echo in the wire coming into the computer. Okay?
Just backing up back to some basic kind of understanding. The echo is, we're not just sampling there. It's not a time to sample. Something is actually happening where current is produced once these electrons all come back to, I guess, what I'm thinking is back to a baseline state, a low energy state. It's all about, no?
This has nothing to do with energy. This has to do with phase. Remember, the reason why you have a non-zero bulk magnetization vector in the XY plane is that the nuclei are spinning around with the same phase. Once they become out of phase, then the XY component of the bulk magnetization vector is zero. The individual spins keep spinning around at the Lamar frequency, but they add up to zero so that there's no bulk magnetization vector.
Well, isn't at time 2 tau bulk magnetization in the XY plane essentially back to zero? Or very close to it?
No, the bulk magnetization vector, if it's zero, you get no signal. It's zero all through in between here. What happens is at the time the echoes that the spins come back into phase, so the bulk magnetization vector is no longer zero. They add up to a real value, and now you get a non-zero bulk magnetization vector in the XY plane, which is spinning around. That will induce current in the receiver coil, and we'll get an echo. Very rapidly, they'll get out of phase again. The bulk magnetization vector in the XY plane goes to zero, and we no longer get a signal. So it's only when the nuclei come back in phase that we get a signal. And the peak of this signal will only go as high as the T2 curve. It cannot go above that. Okay? Okay, Yuri, well, why can the signal get no higher than the T2 curve? Why can't it go back up to the baseline signal that was way up here?
It has to do with the fact that the hydrogens, each hydrogen has its own frequency that they spin at, and those spins interact with each other and attenuate the signal. Basically attenuate the signal. It's diminished by their interaction with each other.
What happens? That's partially correct. They interact with each other, but what that interaction does is it causes a time variation in the strength of the magnetic field at the location of the spins. And if we go back to this diagram, the only reason these different vehicles come back to the starting line at the same time is that they all have the constant speed. As we talked about before, if you go up for an hour in this direction and then you tell them to turn around again, but if the tortoise then hops on a bicycle, then the tortoise is going to start here and it's going to end up way over here, so it's going to go past the finish line before all the other guys come back. Consequently, if the rocket runs out of fuel and it starts slowing down, then all these other guys will come back to the finish line, but the rocket will get there late. So they'll all come back to the finish line at the same time as long as their speeds are the same and never change. If there's any time variation in their speeds, then the time that when they get back to the finish line will be out of phase. So what happens is, and you're right, these nuclei will interact with each other. They'll cause the magnetic field to fluctuate over time, which means these guys won't actually be spinning at exactly the same frequency, and some of them therefore won't be in phase. or they'll only partially be in phase when the echo occurs. And this is irreversibly lost signal, which is the signal difference between the T2 curve and the maximum peak at time t equals 0. That is irreversibly lost signal, and it's due to the fact that the magnetic field isn't constant, it's time varying. If the magnetic field were exactly constant throughout the entire experiment, before the 180-degree pulse and after the 180-degree pulse, then you'd get 100% rephasing, and the signal would go all the way up to the baseline state. So now, why is this important? Now, the T2 star value, if you initially give the 90-degree pulse and you put an oscilloscope on the wire that's coming from your receiver coil, what you will see will be signal variation. You will see a signal here with frequency, if at 1.5 T would be about 64 megahertz, 64 million times a second. So we'd see this wiggle here and it would drop off very rapidly, typically within a couple of milliseconds. There are two components causing that. One is the drop off from the T2, which is the time varying inhomogeneities. The other one, the difference between the T2 curve and the T2 star curve, is the phase variations due to fixed magnetic fields that don't change. But we know if they're fixed magnetic fields and don't change, that when we do the echo, we'll get all that signal back. So the signal from the baseline to the top of our echo is all spins phasing that's due to the fixed magnetic fields. All this that's lost above due to T2 is due to the time varying magnetic fields. And it turns out because the T2 star is the sum of both of them. So T2 star is typically in biologic tissues much faster than T2 because most of the inhomogeneities in biologic tissues are fixed and stay the same over time, which is nice for us because we can get rid of those and just see the T2 time changes. Now, the reason why this is important is that the reason T2 drops, the time varying magnetic fields, are due to the interactions between hydrogen and hydrogen in the molecules. That's all determined by the shape and configuration and motion of the molecules, which is something that's a physical chemical property of the tissues, which is very important. The fixed magnetic field changes down here that cause the very rapid shortening of T2 star typically aren't real important. They tend to be the interfaces like cell membranes and things like that, which allow you to have fixed variations in the magnetic field. And that's why typical gradient echo images don't give very good contrast. You can have a T2 star image and you can have a big tumor there and you can't even see it. Or you can have a big inflammatory lesion or an infection and not see it because T2 star is not as sensitive for the biochemical changes which occur in tissues. So and that's why we found that the T2 weighted images or variations of that we'll talk about later are much more important from a diagnostic standpoint because variations in T2 tell us a lot about the molecules that the tissue is made up of and the water content in those tissues. Okay, is that as clear as mud? Or a little clearer? Uh-oh. Sheila, you all right? That's as good as it's going to get for right now. Okay. Yes.
Can you just repeat one more time the difference?
Dr. Cruz.
So who was the first one who talked? Is that Sean?
Sean, go ahead.
Yeah, I think I jumped in first. I butted in first.
Okay, go ahead, Sean.
Can you just repeat again the differences between the T2 star and T2 between the fixed and non-fixed? I think I got it, but if you would repeat it again, that might help.
Yes. Okay. So let me start a little bit before that. We said, again, what's very important to us is that there is a difference between what happens to the protons that have to do with fixed magnetic field differences, which the echo completely corrects for, and the time-varying magnetic field differences that the echo cannot capture. And that's why the peak of the echo we get is different from being the maximum value. And that's why we can differentiate between tissues based upon T2, because some tissues have a lot of time varying magnetic fields and other tissues don't. And therefore it gives us great contrast for pathology. Now, the difference between T2 star and T2, there are two components to the dephasing of the spins. All of the dephasing is due to the fact that the nuclei, the protons, are in slightly different magnetic fields. That causes all of the dephasing. If the magnetic field were exactly the same throughout the entire tissues, then once you give a 90-degree pulse, you'd have an echo, you would have signal forever. It would never drop off because they would stay in phase and you would never lose phase. So the bulk magnetization vector would just rotate around in the XY plane forever and you'd always have signal. But what happens is that they get out of phase and the signal drops off. And everything that causes inhomogeneity of the magnetic field will cause the T2 star to decay. But only the time varying magnetic fields will actually cause the T2 to decay. So T2 star is both. T2 is only the component due to the time varying magnetic fields. And the reason T2 is important is because it's something we can measure. And the reason we can measure it is because when we get an echo, the height of the echo is limited by the T2 decay curve. And that's how we can measure it. And it's an important variable for us because it's something we can measure. And not only that, it turns out to be important in letting us evaluate the biochemistry of the tissues. Did that answer your question, Sean? No?
Yes, I think so. But like when you do multiple echoes, why doesn't the T2 star reappear into the echo?
Okay. The T2 star here is due to the 90-degree pulse. When you do a 180-degree pulse, we're just flipping the spins 180 degrees. When you do that, you're not forcing the spins into the XY plane. You're just flipping the bulk magnetization vector upside down. If time t is equal to 0, let's say we have an inversion and recovery sequence, which we talked about before. If we put the body in the magnet and then we give a 180-degree pulse, you will flip the bulk magnetization vector from z to negative z, but you'll get no XY component, and therefore you'll get no signal and you'll get no T2 star. So when you put in a 180-degree pulse, all you're doing is flipping the nuclei 180 degrees, and you're not forcing anything into the XY plane, so you don't get any more signal, the T2 star signal.
Okay.
If it's not 180 degrees or a 180 degrees plus n times 360 degrees, anything else is actually going to force some bulk magnetization vector into the XY plane, and then we would get a signal. And we'll see that we do this in steady state free precession type imaging a lot.
Okay.
But we're not there yet.
Okay.
Question.
Let's see. I think Yuri had a question. And then Yuri?
So T2 is time varying, is dependent on time varying magnetic field, and T2
Variation.
star
Yep.
has two components to it. One component is the time varying magnetic field variation, and the second component is the time independent variation.
That's right. And there,
Okay.
time independent, it's a variation over distance, but it's from place to place in the body, but it does not change over time.
Okay. Okay.
And because it doesn't change over time, the 180-degree spin echo will completely correct for it, and we can then get a signal back from those nuclei in the echo. Ram?
Couple of questions. First of all, if when we have the tissue in the magnet before we even give our first 90-degree pulse, and everything goes into the bulk magnetization points in the z-axis. Now, the 90-degree pulse is a short pulse, right? It's a finite pulse you give that throws everything into the XY plane.
It can be as short as long as you want. It's a combination of how long it is and how strong it is. So typically we'll use a short pulse that's relatively strong. So it may last less than a millisecond.
But once it goes into the XY plane, is the bulk magnetization not quickly coming back down from the XY plane into the Z axis
Now,
again?
remember that there are two components. First, the XY goes down to 0, and then the Z grows up in the Z direction. The time it takes for the XY component of the bulk magnetization vector to drop to roughly a third of its maximum value, we call T2. The call it actually, technically, I guess we should call that T2 star. And then roughly two-thirds of the time it takes the Z component to go from 0 to its maximum value, we call T1. So correctly, the time it takes for the XY component to go to about a third of what it is, of its maximum value, is actually T2 star. And that's why we see it dropping here.
So if you didn't have the T2 curve and you just looked at the T2 star and you just did like one echo, then that would be a combination of T2 star and T2. And then
Now,
as you give the 180-degree pulse, you basically leave the T2 star signal because it's no longer in the XY plane, and you're just measuring the T2 signal. Is that correct?
right. Yeah, this first thing is not an echo. This is called the free induction decay.
Induction decay. Mm-hmm.
And you can image off the free induction decay now. Well, that's a challenging thing to do, but you can echo off you can get a signal now off the free induction decay. The reason it's a challenging thing to do is that these big 90-degree pulses, not only do the nuclei see those in the body, but all your receiver coils and electronics can see those also, and it can cause big ringing. This is a much stronger signal than the weak little signal we get back from the nuclei. So typically you shut off all the electronics when you receiver electronics when you give the 90-degree pulse, and you wait for everything to kind of calm down in the electronics. So people tend to keep all of the receivers off until we get close to the echo. But now using very fast technology, you can actually receive signal right after the 90-degree pulse and actually image off the free induction decay, and some types of ultra short imaging, Ute-type imaging, will image off the free induction decay. And those are obviously going to be T2 star weighted images.
Another question. Okay, I guess the one thing conceptually I'm having a little bit of issues with is, so what's going on here, once you put the 180 pulse in and you're waiting for your echo to come back, this is a phenomena that happens, a signal is at that 2 time or T, what is it, 2 times tau, that that the echo comes back. That's just a phenomenon that happens. You're sitting there waiting, sampling for it, and then it hits your coil and it records it.
Yeah, basically, if you kept your receiver on after the T2 star decays down, and if we turned it on here before the 180-degree pulse and listened all the way out, what we would see is a huge signal with the RF pulse. Then there would be no signal for the RF pulse until we get very close to the TE time, which is the 2 tau time here, within a few milliseconds. And then you'd start getting a signal. It would be weak at first. It would grow to a maximum. Then it would become weak again. And then it would go away and you'd have no signal.
And that's the nuclei rephasing.
Yes.
So you need it, once those things come back into rephasing, once those nuclei, the spins rephase, an echo is given off.
And it's what they do. They rephase. Then the bulk magnetization vector goes from 0 in the XY plane to a value in the XY plane. Then once you have the bulk magnetization vector spinning around the XY plane at the Lamar frequency with a non-zero value, you have basically a spinning magnet. And any metal you have in the area, like the coil in a receiver coil, will have a current induced in it, just like we talked about before. So it's that bulk magnetization vector inducing a current in our receiver coil right next to the knee, and then that current in the receiver coil is what you feed into the computer.
I see.
Okay. Any other questions? Okay. Now, if we now think about T2, uh, tissues that have, uh, this is not really quite right, tissues that have long T2 values have one characteristic in common, and that is they tend to have freely moving nuclei. So they tend to be liquids or gases. And liquids and gases are collectively called fluids, right? So fluids tend to have very long T2 times. And the reason for that, whereas solids tend to have very short T2 times. And the reason for that is if you have solids, the nuclei are fixed in space. Now, a solid, it has a lattice structure to it, and that is that the molecules are arranged in three-dimensional space in a very rigid, repeating structure. At least most solids are this way, uh, kind of by definition of a solid. And that means that the nuclei then are basically in the same location with respect to each other. And therefore, if there's an interaction between the two, that interaction is the same and it can produce dephasing, varying but dephasing. If, however, these molecules and nuclei are able to diffuse freely in space, they'll interact with one another at brief times and not at other times, and the average of their interactions will average to zero. Sometimes it'll increase the magnetic field where they are, sometimes it'll decrease the magnetic field, but these time varying fields will then average close to zero. So it turns out then that solids have much more efficient dephasing of the nuclei from spin-spin interactions and tend to have short T2s, whereas fluids tend to have long T2s. So if you have a T2 weighted image, what's the brightest thing on the structure? Well, it's water. It's like fluid in the bladder, or CSF in the spinal canal, or edema in the soft tissues when you have infection, or tumors that have a high amount of free water in their cells. They're not as efficient at cells than normal tissues, so they tend to have a lot of free water, even if it's within their cells, and they tend to be bright on T2 weighted images. Okay? And that's the reason, is that their water molecules are moving freely. Whereas in muscle, normal muscle, the molecules are all tied up in the large molecules and they're not able to move very freely. And that's especially true in tendons or cortical bone. There are water molecules in both tendon and cortical bone, but they're rigidly fixed in space, so they have very short T2 times. So by the time we get an echo, there's no signal, so they're black. If you go to ultra short TE imaging, we can actually get signal, as I'll show later, from cortical bone and from tendons. But with most of our sequences that we use on clinically right now, the TE times of that water is too short for us to be able to detect. I don't know why I have this up here. So just to reiterate it, there are T2 and T2 star, and the T2 is due to time dependent dephasing, and T2 star is due to both. Okay, now we don't need to go through this.
Just real quickly, could you give us an example what like a time-dependent phasing is? Like, are these like we're talking about inhomogeneities in the magnetic field. Is
Right.
that
Yeah.
so? The time independent is just the inherent structure of the tissue and how different molecules interact. So what's the time? That's the time independent. What's the time dependent?
Okay, the time independent is due to the stuff you just talked about, as well as the fact that the magnetic field from our magnets isn't uniform. And we try to make it uniform, but there's enough variation into it but that's fixed in space. That doesn't change. Now, the time varying would be if you have two water molecules and they're near each other, but they're moving a lot while we're taking the experiment. Each of them are magnets. Each of them change the local magnetic field where they are, and therefore the exact magnetic field where one proton is going to vary over time because it's next to another proton from another water molecule that's near it, but it's moving in and out. and therefore varying the magnetic field. Okay?
So almost like
That's why it's called spin-spin interaction. Okay? Uh, Now you can actually measure T2 like you do with a cardiogram study, which is GE's name for it, but you can actually do T2 mapping. And then to get accurate T2s, what you tend to do is you do a bunch of 180-degree pulses or other ways to rephase the spins that we'll talk about later. And you'll get a number of different echoes at different times. But again, they're all limited by the T2 decay. So if you then measure the strength of all of these echoes, you can go back and calculate the T2 decay envelope, and then you can calculate the T2 because that's just e to the minus x times time over T2. So you could then just mathematically calculate what the T2 time is. And then so you can calculate the T2 time for each of the voxels, and then it'll typically say different T2 times are giving a different color code, and then you'll get a color image showing you where there's long T2 and short T2 in a sequence. So that's how you would actually measure T2. And it's great for differentiating tissues because most pathology has increased free water and therefore increased T2 times compared to normal tissues. So it's good for edema, for inflammation, for tumors, and for cysts. And this is just a CT and an old MR scan from the 1980s showing this big tumor that we've already seen before. Very subtle, if at all, seen on an old CT scan, and we can see it very nicely on an MR scan. And then here, this again, old studies, and I've kept these old studies in just to remind people of what we started with when all this started back in the 1980s. This sequence on the right took about 18 minutes to acquire back in those days, and that's why you see the motion artifact. T1, we don't see much in the cord. On the T2, we can see a nice lesion from MS here in the cord, even with these old-fashioned image quality scans.
And that's an old T2, regular spin echo T2.
That's a regular spin echo T2. Yeah. Oops. Okay. Okay. So now let's talk about something that you've all heard about, and that's called magic angle artifact. And you've all probably at some time in the past taken a bar magnet, put a sheet of paper on top of the magnet, sprinkled iron files on it, and you've seen the nice display of the iron files aligning along the magnetic field lines. Right? Has everybody seen that? Anybody not seen it? Okay. So you can see that if you take a magnet, the shape of the magnetic field isn't spherical around the magnet. It's actually oblong in the direction of the magnetic poles, and the shape of that field, which is non-spherical, is called a dipole field, because what you have is a positive end and a negative end, and that's called a dipole. All magnets are dipoles, and that then will produce a nice oval type fields around the magnet. And therefore, if you can see, if you took two magnets end to end and you put the north against the north, they're going to push away from each other, and that's going to be very strong if they're end to end. If you put them on their sides and put north on up and north up on both of them, try to push them together, you won't have as strong of a repulsive force because the field around them is not spherical, it's not uniform. And it just turns out then that if you have ordered structures like tendons, so the water lines up of it in an ordered way, that the interaction between the dipoles of the spins isn't going to be spherical. It's actually going to be ordered, and it turns out that interaction comes out mathematically to be 3 times the cosine squared theta, where theta is the angle difference between the two dipoles directions. If you take two magnets together, what the angle is between the two, -1. And it turns out that this can be minimized at 55 degrees and 125 degrees. Uh, what that means then is that if you have an ordered structure like a tendon and you put it at around 55 degrees to the main magnetic field, as long as that causes ordering of the water molecules within it, at 55 degrees, you'll end up having a, increase in the T2. And that's because you've minimized the interaction between the dipole-dipole interactions. So what this typically means, what you see in tendons then, is the signal intensity that they have on short TE images will vary depending upon their orientation with respect to the main magnetic field. And that you'll get a maximum signal when they're around a 55-degree angle with the main magnetic field. Uh, So, and the reason that you get that is that that tells you that there are hydrogen nuclei within that structure which have short TE times. Because what you're doing is you're lengthening the TE times of these structures, and now you're getting a signal. Before, the TE was too short and all the signal dropped off. So this is just an example. Here's an Achilles tendon. Here's on a gradient echo image, which is a short TE image. Where you get the tendon near 55 degrees, we can see a lot of signal in it. This tendon, however, is a normal tendon. You just get increased signal intensity there due to magic angle artifact. And here we can see it on a T1 weighted image, which is also a short TE. But if we go to an old-fashioned T2 weighted image, where you have a long TE, you only barely see the effect.
What's stir here, right? Or stir now?
I'm sorry, stir. Yeah, stir with the longer TE. That's right.
So the modern T2 weighted images still are susceptible to magic angle.
Yeah, it depends on what the TE is. Modern T2 weighted images that we'll get to later, if the TE is long, then you won't see much magic angle effect. This is the effect that you predominantly see on short TE images.
Dr. Cruz, I'm sorry. Why is the T time? Why is it dependent on short T time? I didn't quite understand.
Okay, what magic angle does is, well, if you have a beaker of free water, no matter how you orient it in a magnetic field, you're going to get the same signal because all the nuclei are randomly oriented with respect to one another and they're all flopping around. If, however, you put water in something that has structure, linear structure, like tendons, where you have these long collagen fibers and the water is absorbed to the edge to the long collagen fibers, so they're all lined up in a preferred direction. It turns out that the efficiency by which the nuclei can interact with each other, to produce the spin-spin interaction, which produces the time-varying magnetic fields that leads to the T2 decay. If you arrange it so that they're oriented at 55 degrees with respect to each other by putting the 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 principal direction of the ordering at a 55-degree angle, then the efficiency of the spin-spin interaction becomes minimum. And if the spin-spin interaction is minimum, that means there's less time-dependent dephasing and the T2 increases. So what turns out in a lot of tendons is that you have water that is adsorbed onto the surface of the tendons. That means that they're not free to move around. As we just talked about, that means that their T2 times are short and typically in the range of a millisecond or two. But if you do a 15 millisecond image, then you're not going to get signal because the T2 time is so short that all that signal drops off. If, however, we orient them at 55 degrees, the T2 time then increases to around 15 to 20 milliseconds. If you now do a 15 millisecond echo, you're going to get signal from all of those. And all of a sudden it goes from black to bright, simply because of the way you ordered it in the magnetic field, because you've decrease the spin-spin interactions and therefore increase the T2 time.
Thank you.
And here's just an example of the supraspinatus tendon that's at 55-degree angles with magic angle artifact. And here's a PD fat sat image showing increased signal intensity here, and this is all due to magic angle artifact. Now, sometimes we call it tendinosis, but at this, if it's just limited to this 55-degree angle, we really shouldn't call it tendinosis. One thing you should still be able to see the surface structures, this black line coming down here. And if we go to the T2 weighted image, that bright area kind of goes away, and we just have the intrinsic longitudinal signal. Now you can do ultra short TE imaging. Here is the cortex of the tibia. This is the receiver coil right here, which is up next to the tibia. And what we see here is something kind of odd. Muscle is fairly dark, marrow is dark. The brightest thing on the image now is the cortical bone. And what this is a TE 50 microseconds. Now, normally we deal with 15 to 100 milliseconds. This is now in microseconds. So it's a much shorter TE than we typically do in clinical imaging. In fact, it's so short that we can actually pick up signal from the bound water that's within the cortical bone. Now, what he did here was actually subtract the longer TE structure. So he basically created images of short TE signal and long TE signal and subtracted the long TE signal so he could only end up with structures that have short TEs in them. But if you do it that way, you can find that there is a lot of water in cortical bone, and you can get signal from that water as long as your TE is short enough so that you can catch it before it decays because it has such short T2 time.
How did the receiver coil end up in the picture? Or did they use the body coil?
No, it's a receiver coil. It's receiving signal from everything here. It's just normally we try to have a field of view that doesn't include the coil in it. But you still have gradients that go all the way across the coil. So you can still localize, as long as the coil can receive the signal, you can still localize it anywhere in the area.
But I thought that's the coil that's receiving it. I thought that's
It is. But remember, the way you localize where the signal is coming from is by the gradients. The gradients go all the way through the coil in the body. So just because there's signal around the coil doesn't mean you can't see it. Now, most of the time, if we include the coil in the images, you get a lot of metal artifact that looks awful. So we try not to do that. We try to image, keep our field of view so that we don't include the coil in the images. But in this particular case, and the reason you don't get a lot of artifact like we normally get with coils is that this is an ultra short TE. And this is just.
So, I'm sorry, in the MRI then? So when we have a shoulder coil on, and it sends the 90 degree, it sends the 180. I thought that's, it's just receiving back what it's like just sent. Or is that from is the electronics in the bore of the magnet or in the periphery is what's receiving it?
No. The coil that you put on, like the shoulder coil, well, there are many types of coils, and we'll talk about those later. But there are two basic different coils. One is a send-receive coil, and one is just a receive coil. In this particular case, they use the body coil to send the signal, and they receive the signal from the coil that you see there. So this was a receive-only coil. That works out well for a lot of things. You can get very uniform signal if you use the body coil. It's usually a very good coil to put in the transmit signal. The problem at high field, if you do that, is then you expose the whole body to RF. And if you're worried about heating up of the tissues, which often is a limiting factor in what pulses you can do, especially at 3T, then you don't want to use the body coil to put the RF in because you're going to be severely restricted on your pulse sequences before you get to, you reach the limit of tissue heating. So most of the time in high field musculoskeletal imaging, we like to use send and receive coils. you can do much higher, much faster imaging with much higher gradients and RF and so forth on the knee if you just use a localized knee coil. Because if you do that kind of imaging with the body coil, uh, you'll uh, uh, you'll have you'll have to you can't do it because you heat the body too much. Remember, especially when you get around 3T, an MR scanner is like a like a big microwave oven, and we kind of have an arbitrary limit. And this was something that I think was first kind of proposed by Frank Shellick and I back in the 1980s, and the FDA kind of took it up. Uh, there are a couple of things in our early safety experiments that we did back in the 1980s. One we used, but at that particular time, we just kind of arbitrarily said we could allow the core temperature to go up by 1 degree centigrade in some of the studies that we published. And that kind of became kind of a standard. And it turns out then that there's a certain amount of energy deposition into the tissues, which will typically limit the core temperature rise to less than 1 degree centigrade. And that's basically more or less what the FDA has used as their limitation for SAR exposure. So by using send receive coils, we can put in much more local energy to that area without risking an elevation of the core body temperature. So that's what we usually use. In this case, I think the send coil was the body coil, and this was just a receive only coil. Okay, and the other thing you can do with these UT images or ultra short T images, here the menisci we can see here in vivo. You can see a lot of structure within the meniscus. It turns out that these are the collagen fibers that we can see right here. These little black dots here are actually microcalcifications. And it turns out when you use this technique, you're much more sensitive for calcium than even a micro CT scanner is. And here's just, we can see these are the hoop fibers that we talked so much about when we talked about the menisci. And you want to keep these intact, because if you don't, then you end up having a floppy meniscus, which is no longer functional. But if you use short enough TE images, you can actually see the internal structure. And here we can see a lot of the internal structure and the normal meniscus. And Graham's now done a lot more studies using high resolution imaging to see a lot of internal structure and the way that the menisci are put together. So just more images of menisci using UT imaging. Let me see, what time do we have here? Okay, why don't we talk a little bit about any questions at this point? We're going to come back and talk a lot more about pulse sequences in the next talk. Okay, let's talk a little bit about contrast agents. There are a number of different contrast agents now in MR, but the bulk of what we use are gadolinium-based contrast. Let's see. I don't remember where we were here. Why don't we, Yuri? Oh, why do we use gadolinium as a contrast agent in MR?
I think it's because it causes shortens T1 times, and
Now, how does it shorten T1 times?
um, I'm not certain how. I'm not certain.
Okay. So, do you know of any special chemical property that gadolinium has that differentiate it from most of the other?
It's a
Uh,
large molecule.
okay, it's a large molecule and it has a large number of unpaired electrons in the outer orbits. Sheila, what do I mean by unpaired electrons in the outer orbits?
Paramagnetic.
Okay, what is paramagnetic?
I think it has a lot of unpaired electrons, then it can easily attract other molecules, like other, kind of like
Okay, there with normal everyday matter, there are really three kinds of there are three kinds of magnetic properties that we have in matter. There's diamagnetic, paramagnetic, and ferromagnetic. There's some other things like super paramagnetic and so forth that we won't get into here. But the three classic ones are diamagnetic, paramagnetic, and ferromagnetic. Uh, Aram, do you know the difference between those three?
Um, just functionally, I think the paramagnetic, actually you could produce signal in an MR machine. You could differentiate between it. Diamagnetic, I think, has no signal, and ferromagnetic is, I don't know, it's black.
What do you mean by signal?
No, I guess the answer is no. There's no way I could like
Okay,
explain it.
most structures that we work with are diamagnetic. And what it means, if you put a diamagnetic structure into a magnetic field, the, the electron clouds, like we've talked about, will reorient their orbits, and they'll actually produce a magnetic field against the main magnetic field, and internally they'll have a lower magnetic field. And that's what almost all structures have that. But there are a paramagnetic structure is something that has something different that's much stronger that overpowers the diamagnetic effect that we've been talking about. And that's if you remember that we talked before that atoms are made up of a central nucleus, which is typically protons and neutrons, and then clouds of electrons spinning around it, and that the electrons all are in very highly specified orbits based upon quantum mechanics. And initially, the first electron that you would put in, let's say, which would be typically a hydrogen atom, which is one proton and one electron, that electron would, if it's at a low energy state, will go into the lowest energy state, which is a spherically symmetric orbit around the proton. If you go to the next atom, which would be helium, you've got two protons and typically two neutrons are in it, and then you have two electrons. Both of those electrons will also go into the lowest energy state, which would be a spherical low energy level, and you'd have two electrons, and they have to be pointed in opposite directions. Now, if you go to the next one, uh, if you have three protons, and you add the third electron, you could only have two electrons in any orbital. It will not accept a third electron. And the two electrons have to be pointing in opposite directions. Their spins have to be in opposite directions. And therefore, the third electron will have to be in the second level of orbitals, which is a much more complex. It's not spherical anymore. And you keep, as you get bigger and bigger atoms, you keep getting larger and larger nuclei with more and more protons, and you start filling up for every proton, there's going to be an electron if it's a neutral atom. And you so have to add all these other electrons, and they become very complicated orbits that are very complex in the probability distribution of the electrons around it. So it turns out that most atoms, if you have an odd number of protons, then the outer shell will have only one electron in it. It will not have another electron pointed in the opposite direction. So then that outer electron will be a little magnet that's spinning around in space. If you put that atom into a magnetic field, that outer electron is actually very strong. It will point in the direction of the main magnetic field, and it will add to the main magnetic field. So if you have unpaired outer electrons, the nuclear moments of those are much stronger than the diamagnetic things that we're talking about before, and they will enhance the magnetic field. Uh, so, so, uh, so if you have a paramagnetic substance and you put it into a magnet, then the magnetic field inside is going to be higher than on the outside. But paramagnetic, if you take the outside magnetic field off, those electrons, the magnetic moment of those electrons will then start pointing randomly in space. And when you take them out of the magnet, it has no intrinsic magnetic field to it. But when you put it in the magnet, then Then you get a diamagnetic effect, which makes it a little magnet that opposes the main magnetic field, and a huge paramagnetic effect, which would enhance the main magnetic field. So a paramagnetic structure becomes heavily magnetized while it's in the magnet. But when you take it out, it's no longer uh, a magnet because the electrons orient themselves only when there's an external magnetic field, which causes them to orient in the same direction. Okay? Now, the gadolinium is what's called a rare earth element. It's a very unique set in the periodic tables where these very complex outer orbits, it turns out that you're in a lower energy state if instead of filling up all the electrons in the orbit so that the next electron will be in the same orbit and point in the other direction and cancel out the magnetic moment of the other electron, it turns out it's a lower energy if the next electron, instead of going into that energy state, goes into the next orbital level. And then you end up with 2, 3, or up to 7 unpaired electrons in the outer shells. And therefore, those rare earth elements are much, much stronger paramagnetic substances than the other ones with odd electrons lower down in the periodic table. So the reason we use gadolinium is it has a very large number of unpaired electrons in the outer shell, and therefore it has a very high paramagnetic moment to it. And therefore, uh, uh, it would be a much stronger impact upon the tissues than other substances. The problem with gadolinium is it's also extremely toxic. So the way to get around that is that you hide it inside a safer molecule, which carries it so that the tissues can't interact with the gadolinium, but the magnetic fields from the paramagnetic electrons can still impact the surrounding tissues. And so that's why it's always complex with a large molecule that kind of shields it. And the stability of that molecule is very important when it comes to risk factors. And the biggest risk factor is probably tissue fibrosis. If you get free gadolinium into the tissues, it's highly irritating, which can lead to chronic fibrosis. And if it dissociates easily from the carrier molecule, then it can be very toxic. Okay, then the last form of magnetic substance, I think we're, and we'll end with this, is ferromagnetic. Michael, what's a ferromagnetic tissue? Like iron.
I think it has so it's carrying a positive charge, so it's lacking. I guess it's lacking electrons in one way or another. I'm not sure exactly.
Yeah, no, most bar magnets don't have electric charge. I mean, you could put some static electricity on them, but they have a magnetic moment to them. What happens with ferromagnetic structures like iron is that uh, if you take iron right now, if you took it out into outer space and you heated it up so it was very hot, causing the nuclei to vibrate so much that they become randomized, then you cooled it down, that iron would not be magnetic. If you take that iron, however, and do an experiment where you do the same thing, you heat it up and you bring in a large magnetic field and you allow the iron to cool in a large magnetic field, the nuclei will want to align in the direction of the magnetic field. And when it cools down below a certain temperature, those nuclear moments get fixed in space. And even when you take off that external magnetic field, that iron bar will stay magnetized and be a permanent magnet. Now, if you take an iron bar right now and like a magnet that you'd buy from a toy shop, if you actually went home and heated it up, so it got very hot, almost to melting, and they cooled it back down again, most of its magnetic field would go away. You'd be left with a magnet that would have the magnetic strength of basically Earth's magnetic field. So the way you make a bar magnet, if you would be to take something that's ferromagnetic like iron, heat it up, put it in a large magnetic field, say a large electromagnet or inside an MR scanner, let it cool down below the critical temperature, and then you'll fix that magnetic field in space so that it'll be a permanent magnet. So, so a ferromagnetic is like a paramagnetic, except it keeps its magnetic field even when you take it out of the magnet. And ferromagnetic materials can be a big problem. Diamagnetic material will not be attracted to a magnet. So if you take something that has like gadolinium and put a beaker next to the main magnet of an MR scanner, it won't be sucked in. But if you take a ferromagnetic object like a pocket knife and put it there, it'll be sucked in, or an O2 tank, or so forth. So ferromagnetism is just a little bit different from paramagnetic in that the way the molecules orientate themselves in space, it's a lower energy level if the electrons all point in the same direction once you cool it down. And they produce large problems in a magnet, as you would expect. They'll distort the magnetic field around objects. They tend to be conductors themselves, so they'll also conduct the RF current and induce a lot of artifacts from the fact that they're magnet. Okay, so that's the basic idea of the three major uh, types of magnetic interaction of tissues. Why don't we come back tomorrow and we can then talk about how gadolinium affects the signal concentration when it's injected into the body. Okay, any questions? Okay, thank you.
Thank you.
Thank you.